Before we talked about going from energies to thermodynamic quantities. To go from energy to enthalpy, you need a 0-point energy and you have to correct for finite temperature. Both of those require knowledge of mass, not a big deal, structure of vibrational frequencies. The vibrational frequency thing is complicated. You can think about that in a completely automatic sense. You can design a procedure which says, I'm going to get a geometry at some level, I'm going to get an energy at some level. This frequency is a very expensive property. You can get this at a much simpler level. Take the frequency you're going to get, add it to the other pieces, you can come out with heats of formation. This can all be done in an automatic fashion. And in fact, Spartan sort of automates this in one step if you really want to do it. I want to just touch on infrared spectra frequencies for a very simple reason. Not because of infrared spectra, but rather because it shows something about how you take the results of a theory and empirically bring it into reality. The infrared spectrum of a molecule is the expansion of the energy in terms of a power series. First derivative, second derivative, higher order. If we're sitting at an equilibrium form, this term is 0. This term is a constant. I can forget about it. And the infrared spectrum is then a function of second derivative and higher derivatives. When everyone does, because it's expensive already, is they assume that this term is 0, and we go strictly, we're looking at a second derivative. In many dimensions, it's the same thing. It's a little more messy. If I calculate the infrared spectrum of a molecule, I've taken a simple steroid progesterone, and the experiment is in black, and the calculation are the red lines. I'm getting a bunch of frequencies. If I show this to a real chemist, they're not going to recognize this. They'll think it's a mass spectrum upside down. And so what do I have to do? Well, I have to do two things. The first thing I have to realize is that if I were to have taken the infrared spectrum at 0 Kelvin or very low temperature, in fact, it would look like this. It would be lines. The width of the lines is line broadening to mixing of rotations. So if you simply put a simple parameter into the calculated data, which is really adjusting for line width, it's fitting to a Lorentzian function. And you can actually get something which is looking nice. Now, it's offset, and it's more offset here than it is here. So it's a non-uniform scale. And what this is, that we've made the assumption of a quadratic function, and the real function is non-quadratic. This is too steep, which means that the second derivative is too big. You could correct for this by calculating higher derivatives, which is very costly. Or you could correct for it simply by scaling. And if you just scale, it's a very tiny number. It's very close to 1. If you just scale, you actually get something that looks very good. Now, the reason I'm bringing this up is that there's nothing wrong with correcting data. There's nothing wrong with that. You just have to be very careful, and you just have to be very well documented on what you're doing.